We are ready for a lab on absorbance of photons, visible photons that is, and wavelength, and some solutions. And the solutions we'll be dealing with are going to be, at first, just our McCormick red dye and blue dye. And then we're going to deal with my favorite indicator of all, which is phenolphthalein. As you can see, I've already made up some solutions of McCormick red and McCormick blue, and I've taken those solutions and put them in a couple of cuvettes. As you can see here, we've got our red and blue dyes in these cuvettes that I had glued together. I used a little bit of super glue and also glued my fingers to it for a while. So let's start off by going to a screen here. I'm going to go to a color band screen. One of the things about all of our displays is that really they only have three colors in them. They've got a red, they've got a green, and they've got a blue. And all the colors that you see, all the ones you see in this lab and everywhere else, which are not red, pure red, green, and blue, are just mixtures of them. They are an optical illusion because we only see these three colors. Our optic nerves have got a red screen, a green screen, and a blue screen on them. And the combination of the intensities of these three colors provide the millions of colors that we perceive.
Color vision isn't really completely understood. There's quite a few things that are still a mystery, but one thing that we do know is that there are three types of nerves that are involved in color vision for humans. Ones that involve and can detect red light, others that can detect a band of green light, and others that detects these wavelengths of blue. Once we get signals from this red, green, and blue in our brain, we somehow compute the millions of colors that humans can see. As a result, you can end up producing images of almost any color you like using red, green, and blue. Here's a typical screen that you'll get on any monitor or phone. And if you look very closely at these screens, you'll see at about 100 magnification that there are not all these colors. There is not these grays, blues, yellows, pinks, and greens. That all you've got is the same thing that your eye has. You have a red, green, and blue, in this case, emitters that give these wavelengths of light. Now, they're not a very specific wavelength. They're a band, but they're a band in the blue, green, and red range. And I've indicated them as being 620, 540, and 460, and somehow the mixtures of these produces the colors that we see. For example, right here, if we look at this section of that image, you'll find that there's, in terms of the values of red, 255 being the maximum for the illumination that they have for these emitting diodes, whether they're organic or solid, is 137, and the green is 169, and the blue is 197, and here's their ratios, and that lets us see this color. Here, if you're looking at a pink, I'll highlight that, and here's the pink that we're talking about. That has a red component of 239, a green component of 211, and a blue component of 224. So we can create any color you want to see based on these three wavelengths. And we're going to use these three wavelengths that your monitor or phone or pad can produce to analyze the colors of solution. So this is sort of nice that we can go with these three colors. Now, if you wanted to analyze something with more colors, you could buy a $10,000 spectrophotometer that can analyze a whole range of wavelengths, 2 nanometers at a time. But considering the limits of our spending, we'll use these three wavelengths.
Since we're dealing with just red and blue, I'm going to switch over to a just red and blue screen. There's our red and blue screen. We're going to look at these solutions, the red and blue solution, in front of these red and blue screens that we have with just those wavelengths. Note, when we've got the white background, you can see the red and blue very nicely. But if I move this up to here, all of a sudden my blue becomes much darker, but my red isn't diminished at all. Down here we get exactly the opposite. The red turns almost a black, and our blue keeps its intensity. This is going to be one of the things that we're going to be interested in when we deal with solutions and find out how concentrated they are. So let's switch over now to my favorite indicator. In this well plate, I've put together some water, and I've soaked one of these wells with water in it, and I've put a strip of PHT paper in it. This is phenolphthalein, and I've got that soaked for quite a while. So the phenolphthalein, which is a white powder, has dissolved in the water and is now in a phenolphthalein solution. So I've got a clear water, which is up here, and down here I've got a phenolphthalein solution. So what I'm going to do next is what phenolphthalein is most famous for. That is, it's famous for being able to turn a beautiful color when it's in a basic solution. I'm going to add some sodium hydroxide to this beaker, which has some phenolphthalein in it. You'll see the infamous and beautiful magenta that's produced when you have a basic solution. It's an acid-base indicator. When its proton is removed from it, it ends up having this just beautiful pink color. One of my favorites. Now you can reverse this. You can put the proton back onto this indicator and the conjugated bonds reform, and you'll get back to a colorless solution. Let me go back to here and add some hydrochloric acid. Here's some hydrochloric acid, about the same number of drops. Oh, no, that was sodium hydroxide. Error. Read the containers twice, and as you can see, it's become an even deeper magenta. Next, I'm going to neutralize that basic solution, adding equimolar amounts of hydrochloric acid. I'm going to need about, my guess is 7 drops. We'll mix the solution up, add a little bit more acid, and voila, there it is, back to clear. We can go back and forth on this quite a bit, but what I'm interested in is in the wavelengths that the phenolphthalein absorbs. In fact, that's the purpose of this experiment, to find out about the absorbance of light, and we'll use that to find out about concentration. So let me get my well plate out again, and I'm going to add some sodium hydroxide to my phenolphthalein solution. This is the solution here. I have 40 drops of water and my phenolphthalein in there, actually 39 drops, and I'm going to add just a drop of sodium hydroxide to this, and there's our beautiful magenta again that you can see. In fact, I think I'll add a second drop to see if I can get a slightly darker solution of that phenolphthalein. This is 1/10 molar sodium hydroxide, and that'll react with all the phenolphthalein that's there. Okay, now we've got our pink, or I think magenta is probably closer to it, in that well. You can pretty well see it here. I'll hold it up to the camera lens, and there's that pink. And now we're going to go to our special spectrophotometer to analyze this magenta. Well, here I've got my reaction plate that I've put into this box that I have. That's going to be my dark room. I just took a banker's box, cut off one segment, and cut a hole at the very, very top. As you can see, I've got the white display on my little iPad, so I've got lighting from the bottom, and that lighting from the bottom will provide the light that goes through my phenolphthalein solution. My next step is to take my camera, cover this up completely, so that this is totally in the dark. My only source of light will be coming up from the bottom, the white light, the red, green, and blue that my iPad produces, and I'm going to take a photo of that phenolphthalein and also the clear solution next to it as a reference, because I've got both the phenolphthalein here, which is in one well, and an equal amount of water in the other well. So my next step is to take that photo with only the bottom lighting, and then we're going to analyze that data and find out what really is going on as red, green, and blue light goes through phenolphthalein. And we'll discuss the absorption values that occur with each. So that's our next step. I'm going to get this in the dark, and I'm going to take a series of photos.
Here's my setup. You can see I've got the banker's box all set up. I've got a little hole cut on the top, and then I covered this section when I actually do the experiment. There's the pad that I've got, and it's all lit up. And when I put my camera on top here, I get a bird's eye view of what's happening as the light from the iPad, in this case the red, blue, and green, all making this white go through my solution. I've already taken the pictures and I've saved them on my computer, and now I'm going to analyze them to see the amount of light that managed to get through the water and the phenolphthalein solutions. So I'm going to use apple pie design that I used before. It's very nice. It gives me an average. I don't have to take a whole bunch of individual pixels. I can just average a certain thing, and my size is going to be just right for this. Very nice program, and I found it very useful. I'm going to go to my file. Here I've got my 3 trials. I've already done trial 1 and trial 2. As you can see, I've moved the pad around a bit so that I wouldn't have the same white background in each try. And I'm going to go now for my 3rd trial and analyze that picture, and here it is. And I've got my phenolphthalein solution, and here I've got my water at the other cell. They're right next to one another, so they should have similar illumination. I'm going to look and see what colors manage to get through. The maximum that can get through is 255. That's the way they run colors on digital systems. And here you can see the red, green, and blue components of this white background. This is where I took this picture, and that's what we have there. I have a spreadsheet. I'll pull that up, and I'm going to record that data. I'm going to move this across. I'm going to put that in trial 3. Now this is the water that I have, the red, green, and blue components for the water, 235. This is a little bit brighter than the other 2. The green component was 231. Yep, a little bit brighter than those first 2 trials. In both cases, there's 224 and 228 in the green, and my blue component was 223. So image is a little bit brighter than before. Now let's see though what the phenolphthalein is like. This was just the water, and we saw the 3 components in it, and now we'll get the phenolphthalein. I'll get right in the center. There it is, that beautiful color, and I'll get my spreadsheet up again and record that data faithfully. 207, again greater than our previous ones, because before we only had a 173 and 184. Our green component, still nothing, not a 0. This solution is opaque to green wavelengths. If you wanted to stop a green laser, this would do it for you. And our blue component is 125. Our highest reading yet of the 3 trials, but that's also because we've got a stronger set of white light in there. As you can see, the red managed to get through pretty well. Of the red, if you had 220, I did a percentage here. This is the average of them. 81% of the red light manages to get through. And only a fraction of a percent of the green manages to get through. And on the blue, you get about half getting through. I'm going to go to this little video I made, though, to show you that dynamically. I'm going to start at the very beginning. Here, we've got that phenolphthalein going into the blue. It's darkened a bit. There you can see the phenolphthalein white, and in the green, nothing gets through. And in the red, you can hardly even see that there's any solution there. If you weren't told that there's a solution just using a red light, you wouldn't know it. It's very transmissible in the red, not in the green. And the blue, that looks about 50%. But of course, we've got to figure it out quantitatively using the pixels in that pixel counter. So that makes sense. Our visual evidence was the same. So red transmittance, a lot. And we'd expect that. It's sort of a pinkish color. Green was stopped, and that's why it was pink. White light was trying to get through, and only a small percent of the green managed to. So as we see the light coming out of it, that green is missing, and we interpret that then as that pink. And of course, this blue is gone too, and that prevents it from being that real pure red. It's the red and blue. But percent transmittance is nice, but in chemistry, we look at exactly the opposite. We look at the absorbance. How much is being soaked up? And the reason we have that point of view is because we're using the amount of photons that are being soaked up as an indication of how much stuff is there. So we want to know how much light is being absorbed, because the more stuff that's there, the more light is going to be absorbed. So there's a direct correspondence between absorbance, how much is being blocked, and how concentrated the solution is. Now, it's a logarithmic relationship. As you can see in my calculation here, it's the log base 10 of this average. So we've got all these values changed into their log values. So our maximum is going to be here at 2.83, where our absorbance is a factor of 2.83. Actually, they make it a negative log. In fact, there it is. You can see that negative there, because otherwise we'd get negative values, which don't make sense. So we've got the negative log of 0.81 is 0.09, and the negative log of 0.51 is 0.29, and then this small percent is a huge absorbance. We like to keep our absorbance in the range of about 1 when we're doing experiments, so that we're not going to extremes. And here's our graph, and the graph is the absorbance. Green is being stopped, it's being absorbed. Red and blue, more so blue than red, is getting through. Now, we did this with an iPad and a camera, but if you were doing this with an $11,000 spectrophotometer, you could come up with a graph that just didn't have the 620 and the 530 to 550 range and the 600 and 630 range. It would give you the wavelengths for each nanometer. If you're spending $11,000, usually has a resolution of 1 nanometer. And our graph is very close to the very expensive one. Here, when we're dealing in the 600s, our absorbance is like nada. The light's getting through, and that's what we indicated. And then when we're dealing with the 540 range, that's where our maximum absorbance is. If you're going to study phenolphthalein's concentration, you'd want to deal with the absorbance in this range, the 540, 530 nanometer range, because this way, if there's any stuff there, you'll be able to pick it up because it's being soaked up. And then, even then, our blue, which we have here about 450, if we look here at about 450, yes, it's showing a blockage, a greater absorbance, but not as much as red. So I think we did a pretty good job, considering that this wasn't an $11,000 spectrophotometer. And here's a way of viewing it. Blue, sort of getting through. Green, stopped. Red, definitely. Now, this is our white light, is created by our screens, the blue, green, and red, because we've got blue, green, and red cones. That is how we detect light. And this would be white, but here, because of the missing green and some of the missing blue, we get that color that is so characteristic of beautiful phenolphthalein when it's basic. So, nice experiment, and you should try it yourself. Use that cell phone for something other than sending text messages.